All right, this video is on the Fundamental Theorem of Calculus Part 1 now. So we're first going to write out the formal math part of it, and then we'll go through what it means and how it works so that it makes a little bit more sense. So the definition says that if g of x is a function that's defined as the integral evaluated from a to x of f of t dt, so notice we have two different letters happening here, then the derivative of that function g of x, so g prime of x equals f of x, right? Or we could say d dx, which is just another way of saying I'm taking a derivative, d dx of that integral equals f of x. So two different types of notation, they mean the same thing. And the question we might ask is, how does this work? Or like, how can I use that? So we just have to think about what we know of how integrals work. So typically when you evaluate an integral by hand, you would find the antiderivative of this function inside here. So if we said that this function here was f of t, then the antiderivative, we usually use the notation capital F of t. And we would evaluate this integral from x to a. That's what we would do. And what that means is that we would take that antiderivative and we would plug x into it, and we would take that antiderivative and we would plug a to it, and we would subtract those two things from each other. All right, so now we're saying that this stuff says that the derivative of this equals f of x. So now I want to say if g of x equals this stuff, then the derivative of g of x would be the derivative of the antiderivative evaluated at x. And we always know that if we do the derivative of something like this, we would do the chain rule, and sometimes, so this could be like the outside function, and then x would be whatever the inside function happens to be. So it might not be an x, it might be x squared, and then we have to multiply it by the derivative of the inside, or it could be some sort of outside function, and the inside function is like 3x to the negative 7 plus 11 or something like that. So we would say minus the derivative of this part times the derivative of the inside function. And if we do that over here, a represents just some constant, some number. So when you take the derivative of some constant, that would be 0, and this whole part would be wiped out. So then we're saying that the derivative, g of x, is the same thing as if we took the antiderivative and then took the derivative of it. So if you, and I'm actually going to erase this. So if you think about how derivatives work and antiderivatives work, I have a pencil on my hand, that's why it's doing that. Okay, so if you had a function and then you took the antiderivative of that function and then you took the derivative of the antiderivative, you would just get back to the original function. So that's how we can say in conclusion that g prime of x is the same thing as f of x. Like, that's how it works. So this part right here is the part that is a practical use for us, is this idea right here. So here are your examples, and I think after we do a couple, this idea will seem a lot less weird. So we're going to find the derivative of g. And we're going to say that first we're going to define the function as the integral evaluated from 0 to x of 1 over t squared plus 1 dt. So if I want to find the derivative of this, then I'm going to go ahead like this set up here. We're finding the antiderivative and then plugging x into it and plugging a into it. So we're going to go ahead and just plug x into this. and multiply it by the derivative of x. So the derivative of x is just 1, so multiply it by 1, minus, I'm going to plug the a in, 1 over 0 squared plus 1 times the derivative of that a value, which is 0. So this part, like I said before, this part would 0 out. That completely disappears because you're multiplying something by 0. And then this, when you multiply it by 1, means that this is 1 over x squared plus 1. And that's your derivative. So again, when I take the derivative of x, I'm taking the derivative of the thing that I plugged in. And the thing that I plugged in, I'm not worried about the 1 over t squared plus 1. That's just getting the x plugged into it. I'm worried about x being the inside function, as that's the thing that I plugged in, and that's why I had a derivative of 1. So if we do a second example, we're going to go ahead and evaluate the same integral, but we're going to go from 0 to 2x so that you guys can see how it would make this problem a little bit different. So here, if I wanted to find the derivative, I would say it's 1 over 2x squared plus 1, and the derivative of 2x is 2. And then I can go ahead and do this part, and the derivative of 0 is 0. And so if I simplify this, that gives me 2 on the top. 2x squared is going to be 4x squared plus 1. And so that's what my derivative is that time. Okay, we're going to do one more using the same integral. So here we're going to go from 0 to x squared. So we're going to say this is 1 over x squared, squared plus 1, times the derivative of x squared is 2x. And if I simplify that, that's going to give me 2x on the top and x to the 4th plus 1 on the bottom. All right, so let's see what happens when we're evaluating it if we don't have a second term that would 0 out like that. So this time we're going to evaluate that integral from x to x squared. So that would mean that we've got 1 over x squared plus 1 times the derivative of x squared, which is 2x, minus 1 over x squared plus 1 times the derivative of x, which is just 1. And so that gives us 2x over x to the 4th plus 1 minus 1 over x squared plus 1, and that would be your derivative this time. Okay, so here's a different example altogether. This time we'll say we're evaluating from x to 1 of the square root of t squared plus 1 dt. So I'm still going to plug the first one in first. So I've got 1 squared plus 1 times the derivative of 1, which is 0, minus the square root of x squared plus 1 times the derivative of x, which is 1. And so this part zeroes out, and that leaves me with negative square root of x squared plus 1. So hopefully you're kind of starting to pick up on how these work. They're pretty simple. So for this one, we're just going to say this is 1 over 2x multiplied by the derivative of 2x. Subtract 1 over x times the derivative of x. And then we just have to simplify it. And so this is 2 over 2x minus 1 over x. And those 2's would cancel, so we really just have 1 over x subtract 1 over x, and that means that our derivative is actually just 0. Those two things canceled each other out. So for this one, we'll go ahead and plug in x squared to start. So I just plugged x squared into the function, then I'm multiplying by the derivative of x squared, which is 2x. And then I'll go ahead and plug pi into the function and multiply by the derivative of pi. So that part just zeroes out. And then this first part can simplify just a little bit. The x up here and one of the x's down there can cancel, and so that would leave just a plain old x on the bottom, and this 2 would typically be brought to the front. All right, and we are going to have a few more examples that we'll do in class tomorrow, where we start to use these but evaluating limits instead, but I think this is enough for you guys to absorb. So, Fundamental Theorem of Calculus, Part 1. Woohoo!